Okay, so what we have done till now is to model pack learning as a very well-defined framework for modeling learning in general, but all the discussion we have had in any detail has been about learning Boolean functions. Let us now step back a bit and try to understand how this framework would work when we apply it to learning in general. So our intention was to model learning as broadly as we can. So in order to model that well, we'll start out by considering a learning problem, we can think of it, modeled in this way as a game. So we have two players in this game named Alice and Bob. And Alice plays the role of our oracle. So Alice provides a number x at random and some fixed way, say a distribution. And Alice has in mind an interval between A and B that Bob has to learn. But Bob doesn't know what A and B are. So any number in that interval is valid. So basically each time Alice throws out an example to Bob, Alice gives a value x and an indicator variable type entity, which is 1 if x is in the interval, 0 if x is not in the interval. So Bob just keeps seeing a stream of these examples. But Bob has to somehow construct a mental image of what the interval actually is that Alice has in mind. Okay? So in order to do this well, let's make a few observations. So clearly, if these intervals are real numbers, Bob will need many guesses, and it's a straightforward argument that a finite number of these examples will not suffice for Bob to learn the interval precisely. Okay? So the second point is, that's the first observation. Okay? Second observation is whatever interval Bob decides is what Alice has in mind. At the end, we can test that interval against Alice's scheme, which is defined by the distribution D, right? In what Alice is using to provide the examples. And we can compute the probability through this by testing that as to how well Bob's interval is matching what Alice wants. So that's the second observation we want to make. So it's not as if we have to walk away and say, Bob did his part, we have an interval, but we don't know how good it is. We can actually be fairly precise in estimating how well Bob's interval matches what Alice had in mind, because Alice is forced to say, given an example, whether it's in the interval or not in the interval. We also know that these are drawn from a distribution. Okay? What we want to do is we can compute this probability, and we would more importantly like for this probability to be small. Okay? So it's as if we can keep running examples through and asking questions of Alice and seeing how well Bob's guesses or Bob's guessed interval or learned interval matches this. And ultimately, if you can keep this game going to an indefinite point, you'll get a very precise probability estimate. Of course, we cannot, so we have to bound it, and our lecture today is about trying to figure out how well we can do with a bounded experiment. So let us consider the following simple algorithm for Bob to try. So Bob keeps seeing examples. Some are in the interval, some are outside the interval. Consider those examples that are in the interval. So of those, take the one that's the smallest, take the one that's the largest. So of those that Bob figured out were in the interval. That gives you a temporary bound on your interval. because Alice has certified that those are in the interval, right? So this temporary bound is something that we will start building up. But how many samples does Bob have to see using this trivial idea before we can conclude that with a good probability, that's the bound we've always been pushing for, Bob has learned what Alice had in mind, but the probability is good. Okay? So, in other words, if M represents the number of sample points that Bob has to look at, what is the optimal value for M for Bob to have learned the interval? We expect Bob to have learned the interval with a high probability, remember that, and hence M is the smallest number that satisfies us, that gives us this value. Okay? So our goal is now to try to see if one can come up with a good value for M such that the probability is also satisfactory in this sense. So now we fall back again, because it's easy to use this very naturally. Let us consider the set of all indicator functions for intervals that we want to learn, and that's our concept class. Remember that we talked about concepts and concept classes a while back. So if you take the interval xy and take their corresponding indicator function I, which equals 1 for inputs within the interval and 0 otherwise, and let us also pick some distribution d over the real line and pick some m samples. So now we are setting the game up. So instead of deciding informally that something is in the interval or not, we will now write it down as an indicator function, and therefore the indicator variable that function produces. Okay? So Bob simply does something very simple. Based on what the current run has shown, if A1 is the smallest and B1, let's say, is the largest value, then the interval defined by A1, B1, for which the indicator values were 1, give you the current best snapshot of the interval that Bob has seen. That's our temporary interval. Now let's do some analysis to see how big M should get before this becomes a good approximation of the real interval, good being defined through our epsilon and delta parameters that we've always talked about. So Alice wanted us to learn AB, and by definition, whatever Bob learned is some subset of that interval. If you're lucky, it's the whole set, but it's some subset. Why? We know that B1 is less than or equal to B. Bob always looks for the upper interval based on indicator values that were 1. So you would never exceed B, otherwise Alice is lying. We don't consider that scenario. And by symmetry, A is less than or equal to A1. So the interval A1, B1 is contained in AB. It would never go out of it. Okay? So that's one local observation we want to make. Now let's look at probabilities. So probability that our hypothesis produces an incorrect label, because remember we are always looking for concepts and hypotheses in the PAC model, is equal to the probability that D produces a positive example, okay, in the intervals either A1 or B1B. So if there is a positive example in those two intervals, we missed, because our interval was A1, B1, whereas there are still elements in those two intervals, and that's the probability we miss our interval. Correct? Okay. So now the error, therefore, is the sum of the probabilities of these examples in these two intervals, which we call L for low and H for high. So these are the two intervals. So error of our hypothesis is using the distribution D, X belongs to L and X belongs to H. Okay? So the picture looks something like this, where you have the real line, and this is I is the interval that we picked, J is the entire concept, so we didn't know about these two pieces, right? So the probability that we are not doing a good job is the probability that, if you can see the colors, we are in the green regions. Okay? So if the probability with these associated with these two intervals is smaller than epsilon by 2, okay, or no larger than epsilon by 2, then we are done, since their sum is less than epsilon. If they're no larger, it's equal to epsilon. Right? So let's just pick one interval and study it to understand if this is true, because pack learnability required us to be, on the one hand, learning with a bound like epsilon, but on the other hand, doing it with a high probability. So first we'll study one part of this question and try to understand how we meet this criteria. So let us define a new point, which is an interval L prime. Okay? So if you look at your old structure, this is J, this was L, and some part of it is L prime. L prime is the interval which is large enough such that a probability of a positive example drawn from L prime alone, okay, is exactly epsilon by 2. It's a big enough interval to allow you to draw things from it with probability. Drawn from L prime is epsilon by 2. So now we have a few cases to consider. Our interval L is a subset of L prime. Okay? Then we are done, since the first term in the error probability is less than or equal to epsilon by 2. Because if this is epsilon by 2 L prime, and V, the interval L, is a subset of L prime, then we're done. Because we are less than epsilon by 2, and therefore we're contained. Now we will consider L prime contained in L, which is a more interesting case. So probability of a sample not being in L prime is 1 minus epsilon by 2, because probability of being in it is epsilon by 2. So, and we have m such samples, correct? That's by definition our parameter. So therefore the probability of missing L prime, that is the chosen L contributes error greater than epsilon by 2 under the distribution D, given L prime is contained in L, is less than or equal to that times m of those events. M events is the probability. And a similar argument holds for H. So the total error of being greater than epsilon is less than or equal to 2 times 1 minus epsilon by 2 to the power m by symmetry. This was for the L term, same thing is true for the H term. Now we want the probability to be smaller than delta, correct? So therefore 2 times 1 minus epsilon by 2 to the power m is less than or equal to delta. And this is a standard fact that's known. 1 minus x is less than or equal to e power minus x. So we just use that as a replacement. So basically write this where x is equal to epsilon by 2 as e, and you get this is that expression is 2 to the e power minus epsilon m by 2 is less than or equal to delta. And if you simplify it, that immediately says m is greater than or equal to 2 divided by epsilon log 2 by delta. So for a given epsilon delta, we can choose m through this relationship for this game to get the desired error bounds. So now we were not learning Boolean functions. We were naturally trying to find intervals, the most canonical learning problem we talked about at the very beginning of this entire topic. And we found out a way of determining that there is a number of examples m that we can find, given epsilon and delta, that you can learn that satisfy the bounds, and hence it's pack learnable. So that's effectively the end of the machine learning topic. Thank you. And the only other concluding statement is pack learning is a particular mathematical model through which you can vary epsilon delta and talk about how well you can learn.